All right, today we're going to go over recursion. Have we done recursion yet?
No. We did a little bit in C++. But
Okay, but not here. Yeah, my classes are starting to meld together. For some reason, I thought we'd done recursion, and I looked back and went,
Same.
Yeah, so after teaching this class so many times, I keep thinking y'all have already learned the material I'm about ready to teach, which is hilarious, but in my mind. But not good what I need to teach. So we're going to go over recursion today. What did you tell you recursion was? What did he tell you? You said you did a little recursion. What was it?
it's pretty much just like when a program going until it eventually reaches like an if statement, cancel that.
Okay.
Like it
Forever going.
It keeps calling on itself.
Keeps calling itself. So recursion is when a function calls itself.
And then it explodes.
I stole these slides from I don't know where because they never gave me a location. So these aren't all mine. But this might be able to help you understand recursion. It's kind of copying to the same function or recursing down. It's like the recursive web, Facebook, what, dig, and what's under there? Stumbled upon, Reddit, and I can't read that. Well, now it looks like a video game right down there.
It just keeps going.
It just keeps going until it finally stops and then it comes back. So it's like all the way down. Oh, we found it. Then back up. So linked lists are self-similar. I'm trying to give you a lot of examples to try and help you think recursively. That picture may help you because you're a lot of images copying down and then you come back up. Another thing that may help you is we talked a little bit about a linked list, which is somewhat recursive because a linked list contains data and then a pointer back to itself, right? So it's kind of a recursive definition because it's either null or a node whose next field references a list of itself. So in a way, it's recursive because it's defined based on its own definition. I haven't figured out where this picture was coming from, but it's like it's recursing down.
Sequence.
What?
It's the Fibonacci sequence.
That one, yeah, that's a recursive sequence. Yes, or it can be defined as a recursive sequence. Oh, that's another pretty one. What is that?
Succulent of some sort.
A what?
Succulent?
Well, this is a map, and then now they're recursing. Oh, okay, this one's a dumb example. Anyways, so recursion definition of operations in terms of itself. So you are defining it by referencing yourself somehow. So it's a little, I guess you could almost call it inception. But anyways, you're coming back to yourself or defining it based upon yourself. So recursive programming is when a method that calls itself to solve a problem. It's equally as powerful as iteration or loops. In other words, anything you can do with loops, you can do with recursion. Okay? So it's actually a pretty powerful, it's a really powerful tool for programming. Certain types of problems it is very well suited for and you should use it. Other types, not so much. But keep that in mind. This is going to be another tool or trick in your bag of tricks to help you solve problems eloquently. And you'll be using this in data structures for all those who go forward. Those who don't, well, just sit, try and deal with it as you can. All right, one problem I've found with recursion is a lot of students are apprehensive of it. I haven't exactly figured out why. I think it's because people don't want to think this way. But a lot of times doing something recursively makes a lot more sense, makes it a lot easier.
They tell us it's bad, like when we first started, like in Alice, they're like, recursion is bad, you shouldn't do it, so you can make your program crash a lot.
That's probably the case in Alice. It would probably make Alice crash.
They just tell us like, don't do it, so then we're just like, well, I guess it's bad.
It's like when you're in first grade and they tell you there's no number less than 0, right? A lot of times you can solve the problem more naturally. The thing about recursion is you can get yourself tripped up if you don't set it up correctly. Leads to eloquent, simplistic short code when used correctly. Many languages are functional, meaning that they do not have loops. Scheme ML and Pascal. Pascal, of course, being probably the biggest one of recent time. You don't have loops. You just define everything recursively. And it will make some of your assignments far easier if you try and do it the recursive way as opposed to the iterative way. Okay. Oh, here's a good exercise. So let's just ask how many students are in the front row. Wow, we have our desks done in columns, but that's okay. But a good example then would, let's say that we wanted to figure out how many people are in this row right here. But fortunately, Stephen can only count himself and ask the person behind him. He can't look all the way down. Sorry, I'm not trying to make it. So what he can do is, okay, I'm one, but then he could ask the person behind you, how many are in your row? Well, Tyler could say, I'm one, but I have someone behind me. So then he could ask, oh, wow. What's your name?
I don't know. I don't know either.
The I don't know name. And then I don't know could say, well, I'm one, and I have no one behind me. So then you could say there's one in total. Then you tell Tyler I'm one in total, and Tyler could say, well, I'm one plus one behind me, so that's two. And then you could say, well, I'm one, and there's two behind me, so I'm one plus two is three. Do you see how it kind of just recursively went down and then back up? All right, that's what this picture was doing. We just did in class. Notice each person can solve a small part of the problem, so you're trying to simplify it by just how is each section solved. So a number of people behind me, if there's someone behind me, ask him or her, and they'll respond value n, so the answer is n plus 1, because we might be 1, then 2, then 3. Okay, there we go. So when you're doing recursion, you must always consider the base case, which is when am I done? Base case here is you're on the front row, so obviously there's no one to recurse up to, so you know to stop. So you always want to make sure you know when to stop your recursion. What if you don't stop the recursion? What do you think would happen?
Just keep going.
It would keep going, and that would be
It doesn't know what to do.
infinite, right. Now with recursion, you're actually going to get a stacked overflow error. It's not going to run indefinitely unless you have some really interesting recursion going on, because every time you call a function, it uses some memory. So eventually you'll run out of memory if you have infinite recursion, and then you usually get a stack overflow error of some sort. Okay. Oh, recursive case. The recursive case is when you actually do your calculation and then call yourself.
I do that.
All right, another example. I like these slides because they gave so many analogies. So if you're going down the stairs recursively, you really just need to know two things.
How to walk.
How to get down one stair and how to recognize the bottom so you don't try and go down another stair when you're at the bottom. You've done that before? Right, okay.
Here we go. Let's take a big step.
So which one of these do you think is the base case?
Recognizing the bottom.
Why is that the base case?
Because the base case is how it is.
How it is. So you knew to end when you're at the bottom. So that's your base case. And then your recursive case is getting down one step. There you go. Notice it didn't care how many steps there were. It just knew to go down one and then at the bottom. No, keep going.
It says one stair. Is that a thing? Is that grammatically correct?
Probably not. Oh, wait. It might be. Maybe it's in a different part of the world. It's correct.
It's like petrol and gas.
Yes, petrol. I get you.
Or pot.
So code may look like the simplest case, compute and return the solution. What would be the simplest case here? You're already at the bottom. Sorry, let me answer that for you. The simplest case, you're at the bottom, right? You're done. You don't need to do anything. Otherwise, divide into smaller problems. Okay, go down the step and then call ourselves or do the recursive call. Okay. So let's see. I'm only doing it this way to help you understand how recursion works. Obviously, you would not want to write a recursive function for print stars. I'm just trying to give you an example so you can understand how you can take your loop and basically transform it into recursion. So the idea here is that you have print stars within, and what is this function doing? How many stars? N stars. And then what does it print?
So,
What? It prints a star N times, and then what happens next?
It breaks out.
Yeah, a new line. Print ln is a new line. So it prints a star along the line, and then when it's done, it prints a new line. So it goes to the next line. Okay. So how can we do this without loops? Oh yeah, can anyone think of how we would do this without loops? Let's go over here. Let's go new Java class, recursive fun. All right, and let's go ahead and do public static void main string args. And let's do the first one. Public static void print stars int n. Print the starts. For int I equals 0, I is less than n, I plus plus, system.out.print. And then afterwards we'll do system.out.println. So if I'm over here and I do print stars, we'll say, yeah, let's do 25. And then right click on this guy. Why does it say there's an error? There we go. Run it, prints a lot of stars, and then a new line. All right. So if I was going to do public static void print stars recursive and n, how would I do this? So print stars 25, and then we'll do print stars recursive 25. So we want that line, basically we want the same number of lines on each one. So we were to run this, obviously our recursive line or function is not doing anything. So how will we solve this? Well, first off, we want to think of the simplest case. What's the simplest case?
no stars.
No stars where n is 0. Okay. So if n, we'll say less than or equal to 0, system.out.println, and then we'll return. All right. So what do we do if n is greater than 0?
Print it out many times. Or call the
What is the basic step here? Printing a star. So let's just print a star. All right, so we can print a star. Then what do we do? If we print a star, how much work did we just complete? One step. So how many more steps do we need to do? N
Minus 1.
minus 1. So how do we do that?
I'd use a loop.
We're not using a loop. Right, you would use a loop. Normally you use a loop for this one. How would you not use a loop in this situation? We printed one star.
Print more stars. Call the function itself.
Call the function itself. Okay. Are you just taking guesses?
No,
Why would you call the function itself?
because it's going to do it over again. If n is
Print stars, recursive. All right, but what are we passing this time?
n minus 1.
Why are we passing n minus 1?
Because we already did it once.
We already did it once.
Print stars is easy.
And y'all did not tell me to comment my code. Oops. The base case simplest is when in simplest is when there are no more stars to print. So then we print a star, recursive case, print a star, and recurse. All right. So someone besides Tyler, what's going on?
I barely use code.
Okay, maybe Tyler, what's going on?
We're doing it recursively.
We're doing it recursively. Why does this work?
Because eventually we'll hit zero.
Eventually you'll hit zero. How will you eventually hit zero?
So it's n minus 1.
Right, so it's decrementing, and each time it decrements, what does it do?
Gets closer.
Prints a star, right. Until we hit zero.
Which makes things kind of go on forever crazy.
True.
But does it go to negative numbers?
It could.
Oh, geez.
All right, so what are the cases? Let's go through the slides just to say it again. The basic case, n equals 1. Okay, with 1 or maybe 0, you could just print out a star. What they did, you print it with 1, you print out a star. With 2, you'd want to print out 2 stars. 3, you want to print out 3 stars. 4, you want to print out 4 stars. Wow, that's getting a little complicated. So that's a little too much right there. So instead, what we could do is n is 1, you just print out 1 star. If it's 2, you print out 1 star and then call itself with just 1, which would go up to this case right here. If u was 3, you print out a star, then print 2 stars, which would go here to this star, then call print stars of 1, and then it'd jump up here. Of 4, print out a star, then print stars of 3, which would jump down here, print a star, go to print stars of 2, jump up there, print stars, print a star, print star 1, and then you go out the base case.
That's kind of annoying.
It is kind of annoying. But you could just print it this way. Your base case is print 1 star, otherwise print a star and then print, minus 1 less. Call ourselves with 1 less. Basically saying we've done 1 step of the work, we now need to do n minus 1 steps. Okay. Cool. What would happen if I did not have the base case here? Keep calling itself. See what happens, just for fun.
Well, I guess it would just print stuff out. Never mind.
No, it does stop.
It goes crazy.
Prints a lot of stars, and then let's see.
It did print stars.
Oh, it did print the star. I'm trying to see if I can get the error. Oh, I didn't tell you. It just usually it says overflow of the stack or something. But
It didn't even have time to say it. It's just like, whoa.
it's just all right. We're done.
That's all I can handle.
All right. Well, whenever you see this, you've overdone the stack. We'll just say that. So we'll get rid of that real quick. There we are. And now we'll run it just to make sure the code still works. Perfect. Okay. What does this function do? Or what's the result of mystery 648? Let's draw this on the
Yeah, that I divided by 2.
All right.
Like 102.
N's less than 10. We just return, is that right? Oh, we return n. Otherwise, oh, we have an else. All right. A equals n divided by 10. And int b equals n mod 10. And then we're calling what? Return mystery of A plus B. All right. Okay. Okay, so when you want to think of actually what's happening in the machine, first you want to think of it, you want to look at the stack. And the first call is what? Mystery of 648. All right. What does A equal? 64. Why is it not 64.8? Oh, people cannot read that at home. One moment. Let me make this a lot bigger. So then A equals 64. All right, good, y'all can read it. And what does B equals? 8. Right. 8. What's it going to do now? Add them together and call mystery, right? So it's going to call mystery of 64 plus 8, which is 72. All right, so that's the end of that call. Now it's doing another call on the stack. Mystery of 72. A equals 7. B equals 2. And then what is it going to do? Add them together and call mystery again, right? Which is 9. All right? So it's going to make that call on the stack. Each time you do a call, it's allocating another piece of memory for all the variables inside the function.
Yeah, wouldn't it just return A?
No, because it has to make the call first. It has to do the call. A equals don't care.
It doesn't.
Well, it doesn't call it.
Yeah, it's less than 10.
Yeah.
Just because it goes here does not mean it doesn't allocate the space for A and B. A and B are still allocated in memory.
So they wouldn't be like null? Then?
So in Java, we're in Java. In C++, the values would be unknown. But in Java, the values are 0. But they are allocated on the stack. They are allocated on the stack because you made a function call. And we would know to return, what are we going to return? In, which is 9. So 9, and return 9, back up to here, and then we know we're returning the mystery of A and B, so it's going to return 9. We're going to put 9 right here. It's going to come up here, and this guy's going to return 9. And notice that he's calling return, so then your stack would finally go up to the top and return the value 9. Did y'all see how that happened? It allocated, allocated, allocated. This was allocated. Once it was done, it deallocated, deallocated, deallocated. The answer is 9. Another way to picture it. See, we did mystery of 72. Then inside of that call, another mystery of 72, which is 9. And then mystery of 9, we knew to just return 9. And then it would flow back up that the final answer is 9. Because notice that we're just returning what the call is. And let's get another one. All right, let's do this one on the board. Right, that returns, oh, it's going to return a formula. All right, this one's going to get nice and complicated. Return 10 times n plus n. And this is only hard to make you think about what's going on. And A equals mystery of what are we doing? N divided by 10, all right. And B equals mystery of in mod 10, and then we're going to return, what are we returning? Wow, 100 times A. 100 times A plus B. Okay, let's do this one. What are we calling it on 348? Bless you again. All right. So what's A? Well, if we're right here, we call A. What do we need to do?
Call mystery again.
Yeah, we need to call mystery again. So we're right here, and we're trying to call mystery because we're on this line. So we're going to now call, what are we calling mystery on?
That result.
Which is 34. All right, so we're calling on 34. Is 34 less than 10?
No.
Nope. So now what do we need to do?
Call mystery.
Call mystery again. So we're on this guy. We need to call mystery again. All right. What are we calling mystery on?
3.
Mystery on 3. A equals 0, B equals 0. And what are we returning?
33.
10 times
Which is 33. So it's going to, we calculate 33, and then we'll return that back to here. All right, so then we have 33. Y'all see what happened there?
Why didn't you return it to the top?
Because it goes down the stack.
Oh.
Now we're at the bottom, we're going to go up one. We're at the call of 34. We just computed A equals mystery of n divided by 10. What do we need to do next?
In B.
Yeah, we need to calculate B. So now the point of execution is right here. And what do we need to do? Call mystery. All right, so we're going to have to call mystery. Notice that this has been deallocated, so we just overwrite it. And we call mystery on what? Mystery on 4. A equals, I'll just say 0, B equals 0. What are we returning? 44, yeah, from this calculation up there. So this is going to come up to B. We're going to put in 44. So this has been deallocated. I'll put an X there just to signify we don't care about it anymore. Maybe that'd be helpful. Now what do we do?
Return 100 times A plus B.
All right. We're going to return, what's 100 times A? A is, so that's 3 plus B. Is it really 100? This should be 1,000. It is 100. All right. $330. Oh no, that's correct. 3300. That's right. Plus 44. So we're going to return that. Where are we returning it to? This is A of the previous call of mystery. So this is going back up to A, and that is 3344. So here's 3344. We don't care about this guy anymore because we're finished. So we just executed A right here. What do we do next? B. And what's B calling?
Mystery.
All right, so we need to do another call. This is a mystery of what? In mod 10. What's in at this point up here? Yeah, mod 10 is 8. So what are we returning? Yeah, return 88. Because 8 is less than 10, so we're going to do 10 times n plus n. All right. Move that back up to here. 88. Put 88 right here. We no longer care about this. We're done with it. Now what do we do after b?
Return.
All right, so we're going to return. Let me erase this arrow because we know we're done with it. What are we returning?
100 times A.
All right, so that's 3, 3, 4, 4, 0, 0 plus b, which is 88. So we're really just returning 3, 3, 4, 4, 8, 8. All right. By the way, in all technicality, this memory, these values are still in memory. They're just not being used. That's why I left them on the stack so you could signify or remember that this is that memory. We just used it. We deallocate it. We don't care. We just overwrite it if we were going to use it again. But hopefully you can see how you can do multiple calls and jump up and down the stack. You can actually get this really, some really deep recursive calls here. Any questions over what I just did here? Nope. All right. So what they did here, another picture of it, mystery 348, int a equals mystery of 34. Okay, we got to call ourselves. A would be mystery of 3, which is 10 times 3 plus 3, which is 33. B is mystery of 4, 10 times 4 plus 4, which is 44, and then we will return, remember, the 3344. Then B is mystery of 8, which is returning 10 times 8 plus 8, and then we know at the end to multiply A by 100 and then add 88. What was this method really doing? Compare the input to the output. Doubling every digit. All right, we're not going to do this exercise. Okay. Let me go and pause there.